ROS supports multiple programming languages for developing ROS nodes. Each language is supported through something called a ROS client library. For C++, that library is called rclcpp. It provides a C++ API for all of the core features of ROS. In this video, we'll cover the basics of creating ROS nodes using rclcpp. Let's get started by adding a bare-bones C++ executable to the RJ training package we created in a previous video. Throughout these videos, I'll be using Visual Studio Code as a development environment, but you can use any editor you'd like. On the left, you can see the RJ training package that we created. Let's go into our source folder and add a new file. We'll call it firstnode.cpp. In this file, we'll create a minimal C++ program. We just created a main function that does nothing and immediately returns. In order to actually build this program when we build our workspace, we need to add it to our build rules in Cmake lists.txt. To do this, we've added 3 lines to our Cmake list file. In the first line, we create a new target named firstNode that compiles our firstnode.cpp file into an executable. In the next line, we associate that target firstNode with all the packages we're going to depend on. In this case, we're just depending on rclcpp, though we can add as many dependencies as we'd like to this line. And finally, we'll install the program built by this target into the runtime destination for our package, which is lib/our package name, which we can get from the Cmake variable project name. Now in the terminal, we can go to our workspace folder and run culkan build. And we'll see that it is actually compiling our firstnode.cpp file. That's good, but we haven't made a ROS node yet. So let's go add some ROS code to our program. Back in firstnode.cpp, we'll start by including the client library header. Now we'll add a few lines to the main function. In our first line, we're calling init. This gives the client library a chance to set up any under-the-hood global resources it'll need to work. Then we create a new node object, giving it the default name we want our node to have in the ROS graph, in this case, firstNode. Note that we're making a shared pointer here, which is something we'll explain in a later video. Then we need to call spin and give it our node. Spin is a function that will loop forever, handling all ROS-related events for us. When we ask the node to shut down, for example by using Control-C in the terminal, spin will return, and we'll then call the shutdown function, which gives the client library an opportunity to clean up any of the resources it created in init. Now that our code actually creates a ROS node, we can build it again and run it by using ROS2 run RJ training firstNode. And it runs, but of course it doesn't actually do anything yet. It just sits there in that spin function until we ask it to stop by pressing Control-C. An important part of developing software is logging the state of our code as it runs, so we can see what the robot was thinking when it does something unexpected. ROS provides a powerful logging system that allows logs to be captured in a variety of ways through standard interfaces. rclcpp provides access to these logging capabilities through a set of macros. Let's add some logging statements to our node. I've added 4 logging statements to our code, so we can see how logs work at different log levels. Note that each macro name specifies the level of the log we're using. We have to give every macro a logger object that we can get from the node, and then we can give it a string message that we'd like to log. The first level, debug, is for logging any details that only really need to be looked at when you're actively debugging a problem. Info is a good general purpose log level for just any status messages that you need to display to the user. Warning is an appropriate level for problems that the code encounters that may or may not actually be real problems that the developer cares about. And the error level is appropriate for any problems that almost certainly require the developer's attention. Let's now build and run our code and see what those log levels look like in the terminal. You can see we get info, warning, and error in different colors representing their log levels. Notice that debug was not included here. Debug messages are normally hidden, though we can ask it to show those messages by rerunning our node and setting the log level. So we'll stop it with Control-C, and we'll rerun the node, but we'll pass it some ROS arguments with ROS args, and set the log level to debug. Now, we indeed get our debug message, as well as all the debug messages being logged by the underlying client library. There are more variations of these macros that provide features like logging a message only when a certain condition is true, or limiting how frequently a given message is actually logged in a high-frequency process. Check out the rclcpp API documentation for details on these variants. Now, while the node object does offer many public functions for interacting with ROS resources, using it in that way quickly can get complicated. So, a more common pattern is to create a class that inherits from node. Let's rewrite our basic node here using that pattern. So I've made a new class, firstNode, that inherits from rclcpp node. We've created a constructor that calls the base class constructor, giving it that same default node name for our ROS graph. And then we've simply logged a message letting our user know that the first node is in fact ready. In the main function, the only thing we've changed is that we're now creating an instance of our first node class instead of the base node class. We can now build and run our node, and we'll get our ready message. Now we can directly access features of the node object while also keeping our own data well organized. The real power of this pattern will make more sense as we start writing nodes that actually do useful things. There's one more convention we can leverage to offer even more flexibility with our new ROS node. Composition in ROS refers to combining multiple nodes into a single process. There are a lot of neat things we can do by strategically grouping nodes into processes. To enable this, we must register our node class as a component. While the details of composition are beyond the scope of this video, writing nodes as components is the recommended way to write all ROS nodes in C++. The nice thing is that in many ways, writing nodes as components is actually easier, as it automatically takes care of our program's main function for us. The first step to using components is adding a dependency on the rclcpp components package. To add this dependency, we'll open up our package manifest, package.xml. We'll add a new depend tag and give it the package name rclcpp_components. Then in our Cmake file, we'll need to add another find package line and again give it the rclcpp_components package name and let it know that this is a required dependency. Now, to turn our node into a component, we'll need to remove the main method, change our Cmake target from an executable to a library, and register it with the components system. And here are the changes we've made to our C++ file. To start, we've added an include line for the register node macro header from the rclcpp components package. Then we've moved our first node class into the RJTraining namespace to match the package name. We had to add a parameter to our constructor that takes in a node options object and passes it to the base class constructor. And finally, we replaced our main function with the rclcpp components register node macro and gave it the class that defines our node. That's all the changes to our C++ code. Now let's take a look at what we had to change in our Cmake file. Over here, we've replaced our executable target with a shared library target that now shares the same name as our package, though it's still just using the same firstnode.cpp source file. On the next line, we're adding dependencies to that target, and we've added rclcpp components to the list of dependencies. Next, we're installing our library target to the library destination folder. And finally, we're using the register node function to tell ROS about our node. We have to tell it what library target the node is in, what the name of the class that defines our node is, and the name of the executable we want it to create for our node. And those are all the changes we need to make. We can now go back to the terminal and build our workspace. With that built, we'll resource our overlay setup script so that it knows about our new library, and run our node from the RJTraining package called firstNode. And we once again get the node is ready message, but we're now using the component style node. That's it for this video. We've written our first ROS nodes in C++, taken a look at the logging macros, and refactored our node into a component. This component form of nodes will serve as the basis for every node we write from here on out.